Our next speaker is Manjil Saikia from Ahmedabad University, who will tell us about partitions. Please go ahead.
Thank you so much, Professor Nathanson, for this opportunity. And I'm, happy to be a part of this conference, although online. So today I'm going to speak about hook length biases in partitions, and I'm going to talk about two recent work, one on L-regular partitions and another on T-core partitions. So I'll explain what these terms mean as we go along, and I'm going to show you some results that we obtained and give you some proof ideas. Um, so this is this is the main question and the outline that I'm interested in talking about. So the question is count hooks of a fixed length across a family of partitions. And the family of partitions that we're interested in are what are called T-regular partitions and T-core partitions. So let's start with what it means when I say hook length of a partition. So for completeness, this is the definition of an integer partition. So an integer partition of n is a sequence lambda such that lambda 1 is greater than equal to lambda 2 and lambda 2 is greater than equal to lambda 3 and so on. And if you sum up all the lambda i's, then if you get n, then we say that lambda is an integer partition of n. And the lambda i's are called the parts of the partition. So for instance, the 7 partitions of 5 are as given in the slide. So we have 5, then 4 plus 1, 3 plus 2, and so on. And sometimes we also consider this multiplicity or the frequency notation of partition. So where lambda 1 to the m1 just means that the part lambda 1 is repeated m1 times. And similarly, the part lambda 2 is repeated m2 times and so on. So for instance, this partition 2 plus 2 plus 1 plus 1 plus 1 would just be 2 to the power 2, 1 to the power 3. So yeah, as I explained, so this is just the multiplicity of the parts, lambda 1, lambda 2, and so on. Now, there is a very nice pictorial way of representing partitions, which is called a Young diagram. So what one does is, if you have the partition lambda 1, lambda 2, and so on, then we draw a left-justified picture such that the first row contains lambda 1 boxes, the second row contains lambda 2 boxes, and so on. So for instance, this figure is the partition 6 plus 3 plus 2 plus 1. So you have 6 boxes in the first row, 3 boxes in the second row, 2 in the third, and 1 in the fourth row. So this is called a Young diagram. And each box in the Young diagram describes what is called the hook number or the hook length. So if you pick any box in the Young diagram, then you count the number of boxes which are to its right and which are immediately below it, plus 1 for the box itself. So basically, you are looking at a particular box and counting all the boxes in that particular row to its right and all the boxes in that column below it and the box itself. So this figure shows all the hook lengths of the boxes in the partition 6 plus 3 plus 2 plus 1. So for instance, if you look at this box, then you have 1 box to its right, 1 box below it, and 1 for the box itself. So you get 3 as the hook length. Now, the question that we're interested in is the following. So we want to fix a family of partitions of n, and we want to sum over all partitions the number of hook lengths, the number of hooks of a particular length. We're not summing over the partitions, but we are summing over the hook lengths of a particular value. And we are interested in looking at the question whether if you have two hook lengths, K1 and K2, then do you have any inequality of the sort that the number of K1 hooks is greater than equal to the number of K2 hooks, or vice versa, or they may be equal in certain cases. So this is the question that we're interested in. And this question originated from the work of Ballantyne, Burson, Craig, Folsom, and Wen. So they studied this question for odd and distinct partitions. So basically partitions where only odd parts are allowed, and partitions where only distinct parts are allowed. And for those of you who know partitions, then you know that this two classes come from a very famous result of Euler, which says that the number of partitions of n into odd parts is equal to the number of partitions of n into distinct parts. So we also note, because it's going to come up again in the next slide, is that odd partitions can also be thought of as partitions where there are no parts which are divisible by 2. So this was the origin of this question. Now let us define the two families that we're interested in this talk. So the first family that I'm interested in is what are called the T-regular partitions, where no part is divisible by T. So if you look at this partition 4, 3, 1, 1, then this is a 5 regular partition because there is no part in this partition which is divisible by 5. Similarly, if you look at 10, 7, 3, 1, this is not a 5 regular partition because the part 10 is already divisible by 5. So we're looking at, when we say we're looking at T regular partitions, we just mean that the parts in the partition are not divisible by the particular number T. Now, the quantity that we're interested in is this B sub Tkn, which is the number of K hooks over all T regular partitions of M. The second family that I'm interested in are what are called T cores. So in this case, we are looking at all hook lengths in the partition. And if there is no hook length, which is divisible by T, then we call that particular partition a T core partition. For example, if we look at this partition 6321, then this is a 4-core partition because there is no hook which is divisible by 4. So this is actually the partition that I showed you 2 slides back. So let me once again show. Yeah, so this is the partition that I showed you, 6321. And if you look at the hook lengths, then you see that there is no hook length which is divisible by 4. So this is a 4-core partition, but this is not a 3-core partition because you have hook lengths which are divisible by 3. So again, the quantity that we are interested in is this A sub Tkn, which is the number of K hooks over all T-core partitions of M. So two quantities we are interested in, B sub Tk and A sub Tk. B is keeping track of the K hooks over all T regular partitions, and A is keeping track of all the K hooks over all T core partitions. So yeah, so this is once again, showing you the definition of a T core partition with the picture here. Okay, so let's go to the first class of partitions, which is L regular partitions. Let me give you some history. So as I already mentioned that this field of looking at hook length biases started with the work of Ballantyne and her co-authors, and they investigated the number of hooks of a given length in odd versus distinct partitions. And then the next year after Ballantyne and her co-authors work, Singh and Burman, they looked at some more general classes of hook lengths where they, instead of focusing on odd partitions, they also looked at partitions where the parts were not divisible by other numbers. For example, they looked at 3 regular partition, and they showed that there are certain inequalities which are satisfied by this quantity B sub 32 and B sub 31. So there were certain conjectures which were given by Singh and Burman, and those were recently proved by Ku and Zhang and He and Liu in 2 separate work, both of these published in the Journal of Number Theory in this year. Singh and Burman, they also obtained, more general classes of formulas. For example, they looked at B sub T plus 1, comma 1 and B sub T1, and they showed that this inequality is satisfied for all T greater than equal to 2. They also conjectured another bias, and this was also confirmed for the case T equal to 3 by Singh, Burman, and Mahanta. And a complete proof was given again very recently by Lin and Zhang. So this is a very sort of fast-moving area in partitions, and the main impetus was given by the work of Singh and Burman, when they looked at hook length biases of T regular partitions. So what we are interested in, so this is a summary of what I mentioned here. So what we are interested in is I want to show you 2 cases of Singh and Burman's result, which were proved combinatorially, but where we give a Q-series proof. And then I want to introduce the first study of hook length biases for T-core partitions. So these are sort of the generating functions for the classes that we're interested in. So B sub 21Q is the generating function of B21, and B sub 22Q is the generating function of B sub 22N, and so on. So these were already obtained by Ballantyne as well as Kim and Singh and Berman. And this is the standard Q-Pokemon symbol that we're using. So the goal is that Singh and Berman prove some of their biases combinatorially and ask for Q-series proofs. And we were able to give the Q-series proofs for those results. But so I'll give you the proof idea. But what is more interesting is that, sometimes in partition theory, sometimes there are certain things which are obtainable by a Q-series proof, which is not really apparent from the combinatorial side, and vice versa as well. So the combinatorial side gives us certain information which is not really transparent in the Q-series proof. And we'll see such an instance appearing very soon. So this is the difference that we're interested in. We are looking at the difference of these two generating functions, and let's call it G sub GQ. And the idea is that we want to look at FQ, which is 1 minus Q to the 6GQ, which is a difference of, products of nice series. And nice is very sort of subjective. Then the idea is that we want to compare this against another series which dominates minus Q, Q, Q coefficient-wise. And we also need an eventually non-decreasing lemma, which kills the remaining signs which appears in this. So once we have the positivity of FQ, then one can just use induction to show that GQ is also positive. So it just boils down to checking 6 residue chains and then checking the initial values G4, G5, and so on up to G9. And in the other case, I mean, if we look at the other generating function that we're interested in, then except for a short combinatorial injection, we have a Q-series proof of this. But what I want to sort of leave you with is that there is a corollary, which is a previously unobserved link in terms of partitions of distinct parts and Hookland biases. So if we look at the difference between these two Hookland biases for T-regular partitions, then it turns out that this difference is actually equal to sum of a certain number of distinct parts partition, where you are not allowing the part 1 and 2, but all the other parts greater than equal to 3 are allowed. So this comes out very naturally from the Q-series proof that we have, which is not very easy to see from the combinatorial description of the result. So this was this part was joint work with Prabhat Talukdar, who was a master's student, and this was published early this year in Innovative Combinatorics and Applications. But I want to show you something related to T-core partitions now. So T-cores are defined by their Hooklands, and so it seems natural that we may want to study Hookland biases for T-core partitions. This was also suggested to us by Berman when we were discussing some of his work related to T-regular partitions. So it's well known, the generating function for T-core partitions is quite well known, and it comes from some work related to representation theory. This is the generating function for the T-core partitions. A sub T is just counting the number of T-core partitions of N. So, I mean, T-core partitions by themselves are quite important because they have deep connections with, representation theory, quadratic forms, class numbers, and so on. And what is new here is that we are looking at a first systematic study of biases inside T-cores. Whereas earlier authors, they focused on T-regular partitions or only distinct parts partitions. So let me show you some of our result. So for example, the first result that we have is the following. So if we look at all the 2 core partitions with 2k plus 1 hooks, then we can give an exact number. So if n is a triangular number, then we have L minus k as this quantity. Otherwise, it's going to be 0. And it's not very difficult to see. So from this, we get a corollary which shows that the difference between 2 of these values is just equal to 1. So let me show you how we get this. So actually, for the 2 core partitions, the generating function is even nicer. And this is what is known as Gauss's identity, and it can be proved by a Jacobi's triple product identity, which just says that T-core partitions, the number of 2 core partitions of n is equal to 1 if n can be represented as a triangular number, and otherwise it's going to be 0. So, yeah, so this is what I just mentioned. So, I mean, you can just, look at it combinatorially and see that how do two hooks arise in a partition. So there are only two ways in which a two hook can arise, and these are the two ways. So either you have a column like this or you have a row like this. These are the only two possibilities. So once we figure this out, we can actually give a combinatorial description of all the two core partitions. So these four properties need to be satisfied. And once we have, these properties, then it's easy to see that we'll have, a partition of this type. So if you look at this partition, which is basically a triangular number, so all the green boxes are one hooks. And if you look at all the blue triangles, these are going to be three hooks and so on. So this gives us the hook length bias that I just showed a few slides back. But let me show you now. Yeah. So there are certain inequalities that three core partitions also satisfy. So for example, this is saying that the number of one hooks in three core partitions is greater than equal to the number of two hooks in three core partition, which is greater than equal to the number of four hooks in three core partition. Um, and again, the idea is similar. So we look at how three hooks can appear in a partition. So these are the four different ways by which a three hook can appear. And again, this gives us some combinatorial description of how you can describe the partition, which is going to be a three core partition. So this needs to avoid these configurations, these four configurations. And basically it boils down to, uh, 7 different classes, and you count each class and look at the number of one hooks, two hooks, and four hooks, and then see how the difference behave. So for instance, one form is shown here, and you can see that the one hooks are formed in the corners, then the two hooks are in the diagonal just near it, and these are the four hooks in this. So it's not very difficult to count the number of one hooks, two hooks, and four hooks once we have the description of the partitions that we want. Right. So we also have a bias for four core partitions counting one hooks and three hooks. And the proof here is slightly more intricate and uses the idea of a region of a hook. So basically, if you look at a hook here, this is a 9 hook. So you are concentrating on the corner box here. Then everything which is sort of, on the shadow of this, so basically going in this direction, that is called the region of that hook. So which is shown in this shaded portion. So this is one of the proof ideas that is used to show the bias in this case. So we also have another type of bias, which is where we are counting the number of K hooks in T core partitions, but we are now excluding certain parts from the partition. So for instance, if we exclude the part 1 and 2, then it turns out that the number of 4 core partitions with one hook is equal to the number of 4 core partitions with 3 hooks and so on. So there are also, inequalities across two different classes of T-core partitions. So for example, this is a 2-core partition, and this is the case for 4-core partitions. And we have a cross sort of inequality in between these two classes. Yeah, so I mean, I can show very briefly the proof idea for the last one because it's more number theoretic. So what we do is we basically look at the generating function for a 4-core partition. And it turns out that the generating function can be written in this form. And what the proof essentially boils down to is showing that we want a equality of this sort. And we just apply a classical result of Dixon, which says that this sort of form represents every n which is not of this particular type. And we just do some, parity argument to show that whatever we have here is actually not of that type. And it follows from here that this inequality is true. So lastly, some open problems. So just a brief summary. So we have for T-regular partitions some closed form generating functions. Then we have some distinct parts partition also coming in one of the results. For T-core partitions, we have basically we're looking at the shapes of the Young diagram. And then we are looking at biases for very particular classes. We don't really have a general bias. And the reason is that, I mean, the number of configurations really increase if we are going to 5 cores, 6 core, and so on. So here is a conjecture for 5 cores. So this is saying that the number of 1 hooks in 5 core partitions of n is greater than equal to the number of 3 hooks in 5 core partitions is greater than equal to the number of 6 hooks in 5 core partitions. Now, the problem with our approach is that this gives us 40 different forms. So brute classification is no longer viable, and we really need new ideas to show this kind of result. Again, going back to the T-regular partitions, a purely analytic proof of this inequality is still missing because there is one combinatorial step which still remains. And Craig, Dawson, and Han have some asymptotic results. So if we are able to figure out the genetic function for A sub tk, then one could also ask for asymptotic results for A sub tk and so on. So thank you so much. This was what I wanted to show you. And these are the archive links for the 2 papers.
Thank you very much for a very nice talk. Are there any questions for our speaker? If not, then we thank Manjil again. And the next talk will be at 4 o'clock in 10 minutes. Thank you.
Thank you.
Hi, Manjil.
Hi, nice to see you.
Yeah, great. Nice to see you. Great talk. Yeah. Yeah.
So Naranga, whenever you want, you can upload your slides. Looks very good. Where is Galesburg in Illinois?
Galesburg, it's a 3-hour drive from Chicago. It's in central Illinois.
Mm-hmm.
Yeah.
So south of Urbana.
North of Urbana.
North of Urbana.
North of Urbana, yeah.
Okay. Okay.